You just saw a beautiful dessert from Joan Roca in which he took a cooled liquid that he took from a rotovap, cooled it in a freezer to a temperature below 0 degrees Celsius, took it to a table, poured it on a dish, and as it poured, it made this remarkable structure of ice. This, on the surface of it, violates several laws of physics that we have described to you up until this point, and you should all be wondering how it can be possible for this to happen. How can you take a liquid, as he apparently claimed to do, cool it below 0 degrees Celsius at 1 atmosphere of pressure, which we've insisted up until this point is the freezing point of water, and why is it that when you pour it on this dish that you get this big mound of ice forming, which is, after all, what was supposed to happen if it's cooled below 0 degrees Celsius, but why didn't it happen in the first place? So the physics behind this is what I'd like to talk about now. So the reason that this occurs is that it turns out it is possible to violate the phase diagrams that we have now so carefully showed you. But the ways that they're violated are very interesting and important and will play an important role in some of the other cooking we will do later on in this course. And so it's important to discuss. So namely, it is possible to here's the phase diagram of water. It is possible to start out in the liquid phase, as Joan did, to move to a temperature below the freezing point and have the material still remain a liquid. How can this happen? So the simple reason, now of course, as we've already told you, the material when it's below 0 degrees Celsius at 1 atmosphere of pressure wants to become ice. It wants to become a solid. But in order to become a solid, it has to form the solid. It doesn't just happen initially, spontaneously. Something has to happen for it to form. And the reason that this is possible is because it hasn't yet had time to form. So to explain this to you a little bit, let me tell you an analogy. Imagine that you're at a sporting event and something really great happens. Some play occurs where the team that you're rooting for wins, and you look up and you want to start clapping spontaneously, but it's very loud around you. So one person starts clapping, and then the person next to you starts clapping because they're also excited, but it's still, the clapping is not loud enough for everyone to start clapping. But gradually, as more and more people start clapping, the noise from the clapping is so loud that the entire auditorium erupts in applause. The same sort of thing happens when you're making ice in the situation that we just described. Namely, so you're below the freezing point of water. One of the molecules in the ice, in the water, because it's still water, realizes, you know what? I don't want to be water. I want to be ice. So it says to its friend, hey, let's be ice. So they get together and they stick, and then more and more of them start to stick together and make ice until eventually there's a lot of ice. So you see, in order for the ice to form, there has to be what scientists call a nucleation event. It's the same as clapping in a crowd. There has to be a nucleation event where the clapping begins and then it takes over everything. And it's the control of those nucleation events that's at the essence of what Joan did. So, you might think that when this little clump of molecules want to form ice, that it's an easy thing for them to do. Because, of course, as we told you, their energy is lower when they're ice, when they're in ice than when they're in the liquid. That's the whole reason that they turn into ice. The jiggling, remember, is less than the sticking. That's the reason that they turn ice. But if you imagine that this little crystal that we have that we're starting to form, the crystal has two parts. There are the molecules that are in the center of the crystal, and there are those that are on the boundary. Now, the ones that are in the center are surrounded by other molecules which are also in ice, so they really feel like they're in ice. So their energy is lower and they're happier. But the molecules on the boundary have a bit of a conundrum, because on one hand, they're next to other molecules that are in ice, but on the other hand, they're next to the background liquid, that is molecules that are in the liquid. So they're neither bound nor free. They're somehow in an intermediate state. Remember, we talked about energy and entropy. They're not minimizing their energy, and they're also not maximizing their entropy, because they're caught in this funny state between these two regimes. And for that reason, it actually costs more energy to put molecules on the surface of the ice crystal than it is to put them either in the middle of the ice crystal or to put them just in the liquid. So having the boundary actually costs energy. Now, when you have a little crystal, like if you imagine, a group of you and your friends in a crowd starting to clap, there are the people in the center, and if it's a little crystal of like 6 or 7 friends, then maybe you're in the center and you're surrounded by all of your friends on the outside. And so most of the people are on the outside, right? You're the only one who's in the middle. But as the group of clapping people grows, then there are more and more people on the inside and fewer people on the outside. That is, the number of people on the inside is more than the outside. And at that point, it becomes more favorable for, that more people are clapping in the clapping example, and in the ice example, it becomes more energetically favorable for the crystal to grow. So the physics of that is why it is hard to basically create ice below the freezing point of water, and is at the essence of Johan's dessert. Now, but this isn't the whole story, and there's sort of one more thing to tell you. So it turns out that actually if you took pure water, very pure water without any impurities or dirt at all, you could ask, and it is possible to calculate, how big of a crystal do you need to form until the influence of the guys on the boundary is no longer significant enough to stop the thing from growing. And it turns out that crystals of that form, of that size, are big enough that they actually won't tend to form with reasonable chance, with reasonable probability, until about minus 45 degrees Celsius or so. It's really way below the freezing point of water. Even though it is energetically favorable for ice crystals to form, the process that triggers them to form doesn't actually occur if the water is perfectly pure until well below the freezing point of water. Now that, of course, contradicts all of our experiences, because I don't know about you, if I take a glass of water and I stick it in the freezer and I come back and I damn well expect it to be ice. So the reason that the thing that resolves this conundrum is that it turns out that most nucleation of solids, for example, in ice, occurs on dirt. That is, there are impurities or dirt or crud or whatever you want to call it that are in the liquid, and those serve as the nucleating sites for the ice crystals to form. And that's the reason that if you were to try to do what Johann did and take a glass of water and put it in your freezer and try to supercool it, you will find it to be impossible to do it. That is, it will always form ice because there's always dirt in your water. It's very hard to get water that is pure enough that there's so little dirt in it that you actually can cool it below the freezing point. But this is what Johann has managed to do in the dessert that he showed us. And so this is the basic physics that governs the violation of the phase diagram that Johann showed, namely that crystals have to nucleate in order to grow, and nucleation can sometimes be a tricky business. We will revisit this idea of nucleation fairly soon in this course when we talk about creating chocolate and tempering chocolate. You will see that the creation of chocolate in the right crystal phase is really all about controlling the nucleation of crystals.